Welcome back to Applied Mathematics. In this video, intercepts and graphing lines. So, as the title suggests, we are going to be graphing lines here. I want to introduce you to the idea of intercepts, how intercepts can be used to your advantage in graphing lines, and how intercepts can be used to interpret what's happening in the graph of a line or the graph of any equation, really. Let me get my head out of the way, and let's start off with a graph of a theoretical practical application. So I want you to imagine that I am rolling a ball down a hill. And at various points in time, I'm measuring the height of the ball and recording it on my graph. And when I do that, I get some data that looks like this. Clearly, this is not the graph of a line, it's the graph of some other sort of curve. But we can interpolate and fill in some of the missing information and get a plot that looks like this. All right, so this is the height of the graph as the y-coordinate, or the height of the ball is the y-coordinate of the graph. The time that the ball has been rolling is the x-coordinate of the graph. The intercepts of a graph are the points where the graph crosses the x or y axis. In this particular graph, I have a point here where the graph crosses the y-axis, and I have a point here where the graph crosses the x-axis. Let's think about physically what is happening at each of those points. Right? As I'm rolling a ball down the hill, this y-intercept is the starting point. That's where the ball was when I started the timer. What was the ball doing when I started the timer? I have no idea. It could be that the ball was held in some contraption that would let it go and allow it to start rolling the instant I hit the start button. It could be that the ball was further up the hill and I waited until it passed a certain point before I hit the start button. I don't know. It could be that the ball was actually cresting the hill there, right? It could be that if you continued this path beyond, you would realize that what happened was I rolled a ball up a hill. I hit the start button on my stopwatch when the ball hit the top, and then watched it roll back down. Then the x-intercept. That's the point where the behavior changed. The ball is no longer falling, it's now rolling along a level surface. So if I'm looking at an artificial hill, right, a plank of wood that I held up, this is where the ball ended up off of the plank of wood and is now rolling across the table. It hit the ground. That's a pretty basic idea here. There's a pretty simple way of understanding what's going on with a graph, but it absolutely is something that can and should be analyzed. Before I continue further, I'm going to jump back over to Desmos. Let's imagine that I don't just have the measurements of the ball rolling down the hill. Let's say that I have an equation that models the height of the ball at a given time. I'm recording my time as x so I can graph it. That gives me a picture of what's happening. One of the things that I love about Desmos is that it understands the value of axis intercepts. It highlights for you the y-intercept, giving you the ability to click it, and the x-intercept, giving you the ability to click that as well. In this particular case, with this kind of an equation, we don't have the tools for finding these intercepts by hand. We have to rely on software like Desmos in order to do that for us. If you continue onward in the applied mathematics sequence, you will come across the ability to do this. This is one of the things that is not that difficult. We're just running low on time on this semester and we can't get to it. But I wanted to mention that it was a thing. All right, coming back to what we're accustomed to. We've been talking about graphing lines. We're looking for linear equations. So let's take a look at a linear equation. Two x plus 5y equals 10. I can find the x-intercept of this equation. The x-intercept is the point where the graph crosses the x-axis. And an ordered pair for a point where the graph crosses the x-axis has some value for x and 0 for y, right? The x-axis is the place where y is equal to 0. So we plug in that y is equal to 0. In this case, I get out that x is 5. Then, because the x-intercept is a point in the coordinate plane, I'm going to write that point as an ordered pair. The x-intercept of this equation is the point 5, 0. I can do the same thing for the y-intercept. The y-intercept is the point where x is equal to 0, right? To cross the y-axis, you have to be where x is equal to 0. So I plug in 0 for x. I solve for y, and I get that y is equal to 2. 0, 2 is the y-intercept of this graph. One of the things that I like about the intercepts method of graphing is that I talked in the previous video about how difficult it can be to find the point that you're trying to plot on the coordinate plane. If you have graph paper, it's not that bad. If you don't have graph paper, you're in a lot of trouble. All right, but here's the point 5, 0. It's on the x-axis, so it's easy to find. Here's the point 0, 2. It's on the y-axis, so it's also easy to find. Given 2 points, I can draw the line. One thing that shows up in this particular problem that makes our life really easy is that we have integer values for the x and y intercept. There is no reason that that has to be the case. We could have had a different equation. Let's take a look at 4x minus 7y equals 12. We can find the x-intercept here. I'll abbreviate intercept INT because I'm lazy and writing the word intercept is just too many letters. All right, the x-intercept is still the place where y is equal to 0 and we seek out a value of x. All right, that's not too bad, 3, 0. I said I was going to do something weird on this one. Well, when we look for the y-intercept, we plug in that x is equal to 0. We get that x is negative 12 sevenths. That's a nice, easy to work with number or something, I guess. When I'm graphing, I'm generally looking at equations where I can assume that everything is exact, because graphing kind of forces you to assume that. We're just going to assume that things work pretty. All of our coefficients are exact values and we're good to go. That doesn't actually happen ever in the real world, but it gives us something that our mathematics brains can latch on to. So I would report this intercept as negative 12 sevenths, but that gives us a bit of a problem because, well, how do you find negative 12 sevenths on a number line? I'll grab out my calculator and I'll say that's approximately negative 1.7. Honestly, negative 1.5 is close enough because when I'm drawing coordinate axes and trying to find a value, I can't really tell the difference between negative 1.5 and negative 1.7. But I know that it's, somewhere around there. 3, 0 is a lot easier. I just realized as I'm doing this that I forgot to actually write the y-intercept as a point. So 0 comma negative 1.7. All right, that gives us something resembling the graph of the line. All right, so hopefully that gives you some insight as to why intercepts are considered useful even when you're not trying to graph by hand, and certainly also gives you some insight as to how to use intercepts as part of the process of graphing. It's a little bit nicer than just blindly flailing about and plotting points. This video is running long, so I don't think I want to try to squeeze in a third example, but I do want to at least mention, when you're graphing a line, you need at least 2 points, right? A line is defined by 2 points. If you don't have 2 points, you don't have a unique line. It's possible to have the graph of a line where the x-intercept and the y-intercept are the same point. That point would be the origin, the place where x is equal to 0 and y is equal to 0. If that happens to happen, sure. If that happens in the graph that you are trying to draw, you resort back to what we talked about in the previous video. Just pick a point at random. Pick a random value of x, plug it in, solve for y. Or pick a random value of y, plug it in, solve for x, whichever makes you happier. It is absolutely something that can happen. I'm not going to go so far as to say it will happen, but it can, and you should be prepared for it. All right, that's all I have on this one. As always, thank you for joining me. I'll see you next time.